Right, we're going to get into our unit on quadratic functions, and we're going to start a little bit with graphing quadratic functions because there's a lot of intuition and understanding we can get from them from a graph. So let's start out by looking at the parent function, which is the simplest quadratic equation, and I hope we all know what it is. The parent function is y, or f of x, equals x squared. This is the simplest quadratic, and all quadratics will have an x squared in them. And to get some intuition about what's going on, let's try squaring different numbers. Squaring means multiplying by itself. So when we do 0 squared, we're doing 0 times 0, which is, of course, 0. When we do 1 squared, it means 1 times 1, which is 1. When we do 2 squared, it is 2 times 2, which is 4. And 3 squared, we should get 9. 4 squared, we should get 16. And I want to take a look at what's happening here. When we have linear functions, they grow by a constant rate. 1, and we add another 1, that's 2, and we add another 1, that's 3, and we add another 1, that's 4. They add by a constant rate for linear functions. But for quadratic functions, it doesn't add by the same amount each time. It adds by 1, then by 3, then by 5, then by 7. It adds by more and more each time, and we can kind of see this in a picture. When we're doing 1 squared, that's a square that has a length of 1. This is where squared comes from. 1 times 1 gives you an area of 1. When you have a square of length 2, 2 times 2 gives you 4 squares. 4 of these little squares will make up a 2 by 2 square. When you have a square with a length of 3, 3 times 3 will give you 9 squares. And these squares have more and more little squares. By the time you get to 5, we're already at 25 squares inside of it. In fact, we know that there's a constant second difference, that the number the rate is growing by is constant. So it'll go up by 3, then 5, then 7, then 9, then 11. Each time this amount will grow by 2. So this one will go up by 9, and going up from 16 by 9 will get you to 25. So squaring something gets bigger and bigger and bigger, and let's look at what that looks like in a graph. Unlike a linear function, which makes a straight line, when x is 0, y is 0. So when x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 4. And we can see that it went up faster here. It's curving upward. The next one will go up even more. It'll go up. When x is 3, the y will be way up at 9. And so it's bending upwards. We call this concave up because it's growing faster and faster and faster. It's bending upwards. Now, another cool thing about quadratics has to do with what happens when you go to negative numbers. When x is -1, if you square a negative number and do -1 squared, that means -1 times -1. And there's a property of negatives we should know, which is that if you do a negative times a negative, it comes out positive. So when x is -1, the y comes out to be +1. And in fact, it'll be the exact same numbers as below. So when x was 2, y was 4. When x is -2, y will be 4. And the reason is -2 times -2 will come out the same as +2 times +2. They will both come out positive. They will both be 4. And so it will be symmetric. We say they have an axis of symmetry because it's the same on both sides. I hope we can see this here, that there is an axis of symmetry. And along that axis of symmetry is the highest or lowest point. In this case, it's at 0, 0. And this point is called the vertex. So quadratics will have a highest or lowest point, and that's because of the way squaring negative numbers and positive numbers gives you the same answer on both sides. So those are some properties of quadratics that will really affect how things go. Now let's take into account the transformations that we should know. If we have this transformation, this is a transformation of the parent function, which was y equals x squared, we should know that if you have inside the parentheses x minus h, this is a shift to the right by h. And if we have outside of the parentheses adding k, that is a shift up by k. And so what will happen is it will keep the same, this shape is called a parabola, and it will keep the same parabola shape, but if we, shift it to the right or up, the vertex, which was at 0, 0, will shift to the right by h and up by k. And so the new vertex will be at hk. So when we are graphing quadratics, we'll always start by looking at like, what did it shift by? And we'll put a point at hk. We'll see that in just a second. The number in front that is multiplying will multiply all the y values. Now, let's take a look at how we graph this using this hk, and we'll leave the a alone for just a second. This is a vertical stretch if it's greater than 1, or a vertical compression if the value is less than 1. We talked about that last unit, and it will apply here. Let's look. Where is the vertex? Well, the vertex is going to be backwards from what this one is. This is the shift left to right. And remember, it's backwards from what you would think. So this is to the right by 2. So the vertex is at 2 and down by 1. So 2, -1. And we can put that on the graph. Now, the way we graph quadratics from there is we treat this as 0. So this is 0 squared is 0 up from here. And from there, it just follows the shape. It's going to make the same shape. And so we're going to do the same thing we did to make this parabola. From here, we did, when we go over by 1, 1 times 1 is 1. 1 squared is 1. When we go over by 2, when x is 2, we do 2 squared is 4. So 2 times 2 is 4, and so we count 4 up from the vertex. When we go to 3, we say that when x is 3, 3 squared is 9. It'll be 9 up from the vertex. And that same thing will be true here. When we're at the vertex, when we go over by 1, we do 1 times 1, which is 1. When we go over by 2, so over by 2, we'll do 2 squared. 2 times 2 is 4, and so we go count up 4 from the height of the vertex. So over by 2, this is when x is 2, the y will be 2 squared, which is up 1, 2, 3, 4. You see how it went up by 1 the first time, and then up by 4. The next one will be when x is 3, 3 away from the vertex, the y will be 9 above the vertex. So I could count up 1, 2, 3, 4, 5, 6, 7, 8, 9. It'll be right here. We can see it's going to make that concave up bending shape. And a nice trick we can do is, because we know it has an axis of symmetry at the vertex, and in this case, the equation of the axis of symmetry is x equals -2. It's always an x value that it's symmetric on the x-axis. On the other side, we can just take each of these points and reflect it across the axis of symmetry. So this point will be, since it's 2 away from the axis of symmetry here, there will be a point of the same height, 2 away on the other side. And so that can make it really quick to graph a quadratic. Why don't you try this one on your own? What is the graph here? What is the vertex? And we should see that the vertex is going to be 3 to the left. Remember, it's backwards from what you would think from our transformations. 3 to the left, so -3. 2 down is -2. So there's a vertex at -3, -2. And then how do we make points from there? Well, 1 squared is 1 on both sides, because it'll be symmetric. Goes up in both directions. Then we go 2 over. So if we go 2 over from the vertex, 2 times 2 is 4. So we count up 1, 2, 3, 4. Oh man, oh my God, guys. Did anybody catch the mistake? I made a horrible mistake over here. I said the vertex was going to be at 2, -1, but I put it at -2, -1. The vertex should have been over at 2, -1. But the same principle would apply. We'll do 1 squared is 1. We'll go 2 over. 2 squared is 4. And that actually hits the right point. And so I apologize, guys. The axis, the vertex, I graphed in the wrong spot. Even though I wrote it right here, I put it in the wrong spot here. And the axis of symmetry should be at x equals +2, not x equals -2. So I apologize for that, guys. So -3, -2. So we count over 2 from the vertex, and we do 2 times 2 is 4. 1, 2, 3, 4, because that's what squaring a number means, is to multiply by itself. We could go over 3, 1, 2, 3, and when we're 3 away, we'll do 3 squared. 3 times 3 is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's where it would go. So I'll just put an arrow to show that it'll keep going up. And I do know that the same distance away from the axis of symmetry will have points on either side. Okay, x minus 2 squared. Where is the vertex going to be? Well, this is 2 to the right. and none up. So it'll still be at 0. So the vertex at 0, 0 will shift 2 to the right, but none up. From there, we just move over and square whatever number we moved over by. What is the x? The x is getting squared. So x is 1 over, 1 squared is 1. When x is 2, 2 squared is 4. When x is 3, 3 squared will be 9. When x is -1, -1 squared is 1. And when x is -2, -2 squared is 4. Now let's add in the a value. So the vertex is still going to be just like we know it. Where's the vertex for this one? Well, the vertex is going to be at 5, 1. 5 to the right and 1 up. Remember, this inside one is backwards. The left and right is backwards from what you might think it would be. And so I'm going to put a vertex at 1, 2, 3, 4, 5, 1. And now this is where the -2 is coming in. This is multiplying times the number you are squaring. And so when I go over by 1, normally 1 times 1, so 1 squared is 1. But that answer is getting multiplied by -2. So 1 squared will be 1, and then it'll get multiplied by -2. So I will actually end up going 2 down instead of 1 up. Same if I go to the left. -1 times -1, -1 squared is 1, but it gets multiplied by -2. So it goes 2 down. When I go 2 over from the vertex, 2 squared is 4, but that answer gets multiplied by -2. And so it'll be -8. So when I'm 2 to the right, it will go down by 8. So I get these numbers by squaring how far over I am and then multiplying by whatever this multiplier is. So down 1, 2, 3, 4, 5, 6, 7, 8. Same on this side. And rather than count it, I'll just make it symmetric across the axis of symmetry. It's a very useful thing to do. Now, we talked before that this is a reflection. So instead of being concave up, this is now concave down. So this is concave down now. It's bending down. And the other thing, so it's bending downwards. The other thing is that I got vertically stretched because this number is bigger than 1. So if you notice compared to the parent function, it's actually thinner than it normally would be. It got stretched. Okay, try this one on your own. Where is the vertex? Well, the vertex is 3 to the left and 1 down. So the vertex is at -3, -1. And now when I do 1 squared, so if I move over by 1, 1 squared is 1, but that gets multiplied by half. So half of 1 is only a half, and that'll be on both sides. When I go 2 over, when the x is 2 away, the x is going to end up getting squared, so 2 squared is 4, and then I have to do half of 4, which is 2. So this multiplier multiplies times the y value after you square it. When I go 3 away, 3 squared is 9, half of 9 is 4.5. 1, 2, 3, 4 and a half. You do need to be able to do this without a calculator. So, it's a good time to practice. Hopefully we feel good about that. Last one, the vertex is at -1, -5, left by 1, down by 5. Remember the inside one is backwards for what you would think. So left by 1, down by 5, and the multiplier is 3. So after I square whatever number it's going to be, I'm going to multiply by 3. So 1 squared, when I go over by 1, 1 times 1 is 1, but that gets multiplied by 3. 3 times 1 is 3. So it's 3 up from here. 1, 2, 3. And you'll notice a nice shortcut you can do is, ooh, that's wrong. I tried to use the axis of symmetry, but I went over 1 this way and 2 this way, and that's not symmetric. You can always get the first point by just looking whatever this number is. Now after that, you have to multiply and square it, but when you go over by 1, it's up by 3. When you go over by 1, it's up by 1/2. When you go over by 1, it's down by 2. So whatever number that is will be correct for the first value. And that's because 1 squared is 1, and 1 times this number will just be whatever this number is. Now that trick only works for the first point. After that, you have to do 2 squared. 2 times 2 is 4. 4 times 3 is 12. It's going to be 12 up. It's going to be way up there. This is very vertically stretched. And that's it for graphing for today, guys.